Chapter 11. The examination of the phenomena of combustion. The alchemists thought that the most effectual method of separating a complex substance into more simple substances was to subject it to the action of heat. They were constantly distilling, incinerating, subliming, heating, in order that the spirit or inner kernel of things might be obtained. They took for granted that the action of fire was to simplify, and that simplification proceeded whatever might be the nature of the substance which was subjected to this action. Boyle insisted that the effect of heating one substance may be, and often is, essentially different from the effect of heating another substance, and that the behaviour of the same substance when heated sometimes varies when the conditions are changed. He takes the example of heating sulphur or brimstone. Exposed to a moderate fire in subliming pots, it rises all into dry and almost tasteless flowers, whereas, being exposed to a naked fire, it affords store of a saline and fretting liquor. Boyle thought that the action of fire was not necessarily to separate a thing into its principles or elements, but in most cases was either to rearrange the parts of the thing, so that new and, it might be, more complex things were produced, or to form less simple things by the union of the substance with what he called the matter of fire. When the product of heating a substance, for example tin or lead, weighed more than the substance itself, Boyle supposed that the gain in weight was often caused by the matter of fire adding itself to the substance which was heated. He commended to the investigation of philosophers this subtle fluid, which is able to pierce into the compact and solid bodies of metals, and add something to them that has no despicable weight upon the balance, and is able for a considerable time to continue fixed in the fire. Boyle also drew attention to the possibility of action taking place between a substance which is heated and some other substance, wherewith the original thing may have been mixed. In a word, Boyle showed that the alchemical assumption, fire simplifies, was too simple, and he taught by precept and example that the only way of discovering what the action of fire is, on this substance or on that, is to make accurate experiments. "I consider," he says, "that, generally speaking, to render a reason of an effect or phenomenon is to deduce it from something else in nature more known than itself, and that consequently there may be diverse kinds of degrees of explication of the same thing." Boyle published his experiments and opinions concerning the action of fire on different substances in the 70s of the 17th century. Stahl's books, which laid the foundation of the phlogistic theory, and confirmed the alchemical opinion that the action of fire is essentially a simplifying action, were published about 40 years later. But 50 years before Boyle, a French physician named Jean Rey had noticed that the calcination of a metal is the production of a more complex from a less complex substance, and had assigned the increase in weight which accompanies that operation to the attachment of particles of the air to the metal. A few years before the publication of Boyle's work, from which I have quoted, John Mayo, student of Oxford, recounted experiments which led to the conclusion that the air contains two substances, one of which supports combustion and the breathing of animals, while the other extinguishes fire. Mayo called the active component of the atmosphere fiery air, but he was unable to say definitely what becomes of this fiery air when a substance is burnt, although he thought that, in some cases, it probably attaches itself to the burning substances, by which, therefore, it may be said to be fixed. Mayo proved that the air wherein a substance is burnt, or an animal breathes, diminishes in volume during the burning or the breathing. He tried, without much success, to restore to air that part of it which disappears when combustion or respiration proceeds in it. What happens when a substance is burnt in the air? The alchemists answered this question by asserting that the substance is separated or analysed into things simpler than itself. Boyle said, "The process is not necessarily a simplification. It may be, and certainly sometimes is, the formation of something more complicated than the original substance, and when this happens, the process often consists in the fixation of the matter of fire by the burning substance." Rey said, Calcination of a metal, at any rate, probably consists in the fixation of particles of air by the substance which is calcined. Mayow answered the question by asserting, on the ground of the results of his experiments, that the substance which is being calcined lays hold of a particular constituent of the air, not the air as a whole. Now, it is evident that if Mayow's answer was a true description of the process of calcination or combustion, it should be possible to separate the calcined substance into two different things, one of which would be the thing which was calcined, and the other would be that constituent of the air which had united with the burning or calcining substance. It seems clear to us that the one method of proving the accuracy of Mayow's supposition must be to weigh a definite combustible substance, say a metal, to calcine this in a measured quantity of air, to weigh the product and to measure the quantity of air which remains, to separate the product of calcination into the original metal and a kind of air or gas, to prove that the metal thus obtained is the same and has the same weight as the metal which was calcined, and to prove that the air or gas obtained from the calcined metal is the same, both in quality and quantity, as the air which disappeared in the process of calcination. This proof was not forthcoming until about a century after the publication of Mayow's work. The experiments which furnished the proof were rendered possible by a notable discovery made on the 1st of August 1774 by the celebrated Joseph Priestley. Priestley prepared many airs of different kinds, by the action of acids on metals, by allowing vegetables to decay, by heating beef, mutton, and other animal substances, and by other methods. He says, "Having procured a lens of 12 inches diameter and 20 inches focal distance, I proceeded with great alacrity to examine by the help of it what kind of air a great variety of substances, natural and factitious, would yield. With this apparatus, after a variety of other experiments, on the 1st of August 1774, I endeavoured to extract air from mercurius calcinatus per se, and I presently found that by means of this lens air was expelled from it very readily. Having got about 3 or 4 times as much as the bulk of my materials, I admitted water to it, and found that it was not imbibed by it. But what surprised me more than I can well express was that a candle burned in this air with a remarkably vigorous flame. I was utterly at a loss how to account for it." The apparatus used by Priestley in his experiments on different kinds of air is represented in Fig. 16, which is reduced from an illustration in Priestley's book on airs. Priestley had made a discovery which was destined to change alchemy into chemistry, but he did not know what his discovery meant. It was reserved for the greatest of all chemists, Antoine Lavoisier, to use the fact stumbled on by Priestley. After some months, Priestley began to think it possible that the new air he had obtained from calcined mercury might be fit for respiration. To his surprise, he found that a mouse lived in this air much longer than in common air. The new air was evidently better or purer than ordinary air. Priestley measured what he called the goodness of the new air by a process of his own devising, and concluded that it was between 4 and 5 times as good as common air. Priestley was a thoroughgoing phlogistian. He seems to have been able to describe the results of his experiments only in the language of the phlogistic theory, just as the results of most of the experiments made today on the changes of compounds of the element carbon cannot be described by chemists except by making use of the conceptions and the language of the atomic and molecular theory. The upholder of the phlogistic theory could not think of burning as possible unless there was a suitable receptacle for the phlogiston of the burning substance. When burning occurred in the air, the part played by the air, according to the phlogistic chemist, was to receive the expelled phlogiston. In this sense the air acted as the pabulum, or nourishment, of the burning substance. Inasmuch as substances burned more vigorously and brilliantly in the new air than in common air, Priestley argued that the new air was more ready, more eager, than ordinary air to receive phlogiston, and therefore that the new air contained less phlogiston than ordinary air, or perhaps no phlogiston. Arguing thus, Priestley, of course, named the new aeriform substance dephlogisticated air, and thought of it as ordinary air deprived of some, or it might be all, of its phlogiston. The breathing of animals and the burning of substances were supposed to load the atmosphere with phlogiston. Priestley spoke of the atmosphere as being constantly vitiated, rendered noxious, depraved, or corrupted by processes of respiration and combustion. He called those processes whereby the atmosphere is restored to its original condition, or depurated, as he said, dephlogisticating processes. As he had obtained his dephlogisticated air by heating the calx of mercury, that is, the powder produced by calcining mercury in the air, Priestley was forced to suppose that the calcination of mercury in the air must be a more complex occurrence than merely the expulsion of phlogiston from the mercury. For if the process consisted only in the expulsion of phlogiston, how could heating what remained produce exceedingly pure ordinary air? It seemed necessary to suppose that not only was phlogiston expelled from mercury during calcination, but that the mercury also imbibed some portion, and that the purest portion, of the surrounding air. Priestley did not, however, go so far as this. He was content to suppose that in some way which he did not explain, the process of calcination resulted in the loss of phlogiston by the mercury, and the gain by the dephlogisticated mercury of the property of yielding exceedingly pure or dephlogisticated air when it was heated very strongly. Priestley thought of properties in much the same way as the alchemists thought of them, as wrappings or coverings of an essential something from which they can be removed and around which they can again be placed. The protean principle of phlogiston was always at hand, and by skilful management was ready to adapt itself to any facts. Before the phenomena of combustion could be described accurately, it was necessary to do two things: to ignore the theory of phlogiston, and to weigh and measure all the substances which take part in some selected processes of burning. Looking back at the attempts made in the past to describe natural events, we are often inclined to exclaim, "Why did investigators bind themselves with the cords of absurd theories? Why did they always wear blinkers? Why did they look at nature through the distorting mists rising from their own imaginations?" We are too ready to forget the tremendous difficulties which beset the path of him who is seeking accurate knowledge. To climb steep hills requires slow pace at first. Forgetting that the statements wherein the men of science of our own time describe the relations between natural events are and must be expressed in terms of some general conception, some theory of these relations, forgetting that the simplest natural occurrence is so complicated that our powers of description are incapable of expressing it completely and accurately, forgetting the uselessness of disconnected facts, we are inclined to overestimate the importance of our own views of nature's ways, and to underestimate the usefulness of the views of our predecessors. Moreover, as naturalists have not been obliged in recent times to make a complete renunciation of any comprehensive theory wherein they had lived and moved for many years, we forget the difficulties of breaking loose from a way of looking at natural events which has become almost as real as the events themselves, of abandoning a language which has expressed the most vividly realized conceptions of generations of investigators, of forming a completely new mental picture of natural occurrences, and developing a completely new language for the expression of those conceptions and these occurrences. The younger students of natural science of today are beginning to forget what their fathers told them of the fierce battle which had to be fought before the upholders of the Darwinian theory of the origin of species were able to convince those for whom the older view, that species are and always have been absolutely distinct, had become a matter of supreme scientific and even ethical importance. A theory which has prevailed for generations in natural science, and has been accepted and used by everyone, can be replaced by a more accurate description of the relations between natural facts only by the determination, labour, and genius of a man of supreme power, Such a service to science and humanity was rendered by Darwin. A like service was done more than 3/4 of a century before Darwin by Lavoisier. Antoine Laurent Lavoisier was born in Paris in 1743. His father, who was a merchant in a good position, gave his son the best education which was then possible in physical, astronomical, botanical, and chemical science. At the age of 21, Lavoisier gained the prize offered by the government for devising an effective and economical method of lighting the public streets. From that time until on the 8th of May 1794, the government of the Revolution declared the Republic has no need of men of science, and the guillotine ended his life, Lavoisier continued his researches in chemistry, geology, physics, and other branches of natural science, and his investigations into the most suitable methods of using the knowledge gained by naturalists for advancing the welfare of the community. In Chapter 6 I said that when an alchemist boiled water in an open vessel, and obtained a white earthy solid, in place of the water which disappeared, he was producing some sort of experimental proof of the justness of his assertion that water can be changed into earth. Lavoisier began his work on the transformations of matter by demonstrating that this alleged transmutation does not happen, and he did this by weighing the water, the vessel, and the earthy solid. Lavoisier had constructed for him a pelican of white glass, with a stopper of glass. He cleaned, dried, and weighed this vessel. Then he put into it rain water, which he had distilled 8 times. He heated the vessel, removing the stopper from time to time to allow the expanding air to escape, then put in the stopper, allowed the vessel to cool, and weighed very carefully. The difference between the second and the first weighing was the weight of water in the vessel. He then fastened the stopper securely with cement, and kept the apparatus at a temperature about 30 degrees or 40 degrees below that of boiling water for 101 days. At the end of that time a fine white solid had collected on the bottom of the vessel. Lavoisier removed the cement from the stopper and weighed the apparatus. The weight was the same as it had been before the heating began. He removed the stopper. Air rushed in with a hissing noise. Lavoisier concluded that air had not penetrated through the apparatus during the process of heating. He then poured out the water and the solid which had formed in the vessel, set them aside, dried and weighed the pelican. It had lost 17 4/10 grains. Lavoisier concluded that the solid which had formed in the water was produced by the solvent action of the water on the glass vessel. He argued that if this conclusion was correct, the weight of the solid must be equal to the loss of weight suffered by the vessel. He therefore separated the solid from the water in which it was suspended, dried, and weighed it. The solid weighed 4 9/10 grains. Lavoisier's conclusion seemed to be incorrect. The weight of the solid, which was supposed to be produced by the action of the water on the vessel, was 12½ grains less than the weight of the material removed from the vessel. But some of the material which was removed from the vessel might have remained dissolved in the water. Lavoisier distilled the water, which he had separated from the solid, in a glass vessel, until only a very little remained in the distilling apparatus. He poured this small quantity into a glass basin, and boiled until the whole of the water had disappeared as steam. There remained a white, earthy solid, the weight of which was 15½ grains. Lavoisier had obtained 4 9/10 plus 15½, which equals 20 2/5 grains of solid. The pelican had lost 17 2/5 grains. The difference between these weights, namely 3 grains, was accounted for by Lavoisier as due to the solvent action of the water on the glass apparatus wherein it had been distilled, and on the glass basin wherein it had been evaporated to dryness. Lavoisier's experiments proved that when distilled water is heated in a glass vessel, it dissolves some of the material of the vessel, and the white earthy solid, which is obtained by boiling down the water, is merely the material which has been removed from the glass vessel. His experiments also proved that the water does not undergo any change during the process, that at the end of the operation it is what it was at the beginning, water and nothing but water. By this investigation Lavoisier destroyed part of the experimental basis of alchemy, and established the one and only method by which chemical changes can be investigated, the method wherein constant use is made of the balance. Lavoisier now turned his attention to the calcination of metals, and particularly the calcination of tin. Boyle supposed that the increase in weight which accompanies the calcination of a metal is due to the fixation of matter of fire by the calcining metal. Ray regarded the increase in weight as the result of the combination of the air with the metal. Mayow thought that the atmosphere contains two different kinds of airs, and one of these unites with the heated metal. Lavoisier proposed to test these suppositions by calcining a weighed quantity of tin in a closed glass vessel, which had been weighed before and should be weighed after the calcination. If Boyle's view was correct, the weight of the vessel and the tin would be greater at the end than it was at the beginning of the operation, for matter of fire would pass through the vessel and unite with the metal. If there was no change in the total weight of the apparatus and its contents, and if air rushed in when the vessel was opened after the calcination, and the total weight was then greater than at the beginning of the process, it would be necessary to adopt either the supposition of Ray or that of Mayow. Lavoisier made a series of experiments. The results were these. There was no change in the total weight of the apparatus and its contents. When the vessel was opened after the calcination was finished, air rushed in, and the whole apparatus now weighed more than it did before the vessel was opened. The weight of the air which rushed in was exactly equal to the increase in the weight of the tin produced by the calcination. In other words, the weight of the inrushing air was exactly equal to the difference between the weights of the tin and the calx formed by calcining the tin. Lavoisier concluded that to calcine tin is to cause it to combine with a portion of the air wherein it is calcined. The weighings he made showed that about 1/5 of the whole weight of air in the closed flask, wherein he calcined tin, had disappeared during the operation. Other experiments led Lavoisier to suspect that the portion of the air which had united with the tin was different from the portion which had not combined with that metal. He therefore set himself to discover whether there are different kinds of airs in the atmosphere, and, if there is more than one kind of air, what is the nature of that air which combines with a metal in the process of calcination. He proposed to cause a metallic calx, that is, the substance formed by calcining a metal in the air, to give up the air which had been absorbed in its formation, and to compare this air with atmospheric air. About this time Priestley visited Paris, saw Lavoisier, and told him of the new air he had obtained by heating calcined mercury. Lavoisier saw the great importance of Priestley's discovery. He repeated Priestley's experiment, and concluded that the air or gas which he refers to in his laboratory journal as l'air de phlogistique de Monsieur Priestley was nothing else than the purest portion of the air we breathe. He prepared this air and burned various substances in it. Finding that very many of the products of these combustions had the properties of acids, he gave to the new air the name oxygen, which means the acid producer. At a later time, Lavoisier devised and conducted an experiment which laid bare the change of composition that happens when mercury is calcined in the air. He calcined a weighed quantity of mercury for many days in a measured volume of air, in an apparatus arranged so that he was able to determine how much of the air disappeared during the process. He collected and weighed the red solid which formed on the surface of the heated mercury. Finally, he heated this red solid to a high temperature, collected and measured the gas which was given off, and weighed the mercury which was produced. The sum of the weights of the mercury and the gas which were produced by heating the calcined mercury was equal to the weight of the calcined mercury, and the weight of the gas produced by heating the calcined mercury was equal to the weight of the portion of the air which had disappeared during the formation of the calcined mercury. This experiment proved that the calcination of mercury in the air consists in the combination of a constituent of the air with the mercury. Mayow's supposition was confirmed. Lavoisier made many more experiments on combustion, and proved that in every case the component of the atmosphere which he had named oxygen combined with the substance, or with some part of the substance, which was burned. By these experiments the theory of phlogiston was destroyed, and with its destruction the whole alchemical apparatus of principles and elements, essences and qualities, souls and spirits, disappeared. End of chapter 11.